I can't hear you if you're saying something.
I was talking to you all and I was muted. I took my video, started my video, didn't unmute myself. How are you doing today? That's all I was saying. How are you all doing today?
I'm good.
Cold.
Cold.
Cold. All right. So I gave you all some problems at the end of class last time to see just how you would do with this. We had done just a few examples, and I had shown you how we can use these properties of logs along with this change of base formula in our calculator to pretty much solve all types of equations where our variable appears up in the exponent. So I'm curious to know how these went and if I should go over any of this. What do y'all think? Did it go okay, or did y'all have any issues? Am I still muted?
Could you go over, wait, I'm sorry, can you pull them back up just so I can see what, yeah, can you go over number 5 and number 6?
Yes. All right, so let's start out here with this first one, number 5. So the main idea here is we're trying to figure out what x is, right? So the first step for this is to look at where the x appears. It appears as the exponent on e to the x. So we want to first get e to the x by itself. So we're just going to do some algebra here. We're going to subtract 3 on both sides. That'll give us 39 over here. And over here we have e to the x, right? Now, going back to last class, let me bring up how I did one of these. Whenever you have an equation where you're trying to solve for the variable, what we're going to do is we're going to convert this into a logarithm. And then once we do the logarithm, we'll use our calculator. So you have to go back to this idea of what a logarithm is. And so when you have a logarithm, let's say you had something like that I told you about, this thing called the loop, where you take the base there, a, and you raise it to this, and that will be equal to this. In other words, you can convert that over to an expression that looks like this: a to the y equals x. So in this, when we're looking at e to the x equals 39, what we want to do first is convert it to a logarithm. So we want to go from this expression, from the right, the expression on the right here, we want to switch this back to this. So we'll start by writing log, and then we look at what the base is. Okay, so the base here is the thing on the bottom that's being raised to a power. For us, what's the base on this equation? What's the thing that's being raised to the power?
Is it e?
It's e. Okay, so we're going to put log base e. Okay. And then what I like to do is I like to put an equal sign. I think about this loop here. I'm going to have to take that and raise it to some power. So what is that e being raised to here in this equation? What is it being raised to?
$39.
I'm sorry?
Is it 39?
Well, look at the e. The e is the base, right? What is it being raised to? What power is it being raised to? X, right? E is being raised to x. I will put x over here then. Think about the loop. When I do e raised to that power, I need it to be equal to this number that's in here. This is where the 39 is going to go. See, all we're doing here is we're taking an expression and we're converting it to a log. So when you convert it, just go back and think about, oops, think about the loop. If I were to ask you to do this little loop on this right now, you would take E, you'd raise it to the X, right? You would take E, raise it to the X, and set it equal to 39. Isn't that what we have right here? Isn't that exactly what this says? E raised to the X equals 39. So I've written it down correctly. Let me show you. What if you did this instead? What if you wrote this down? This would not be correct, because here, if you do the loop, it's E raised to the 39 equals X. And that's not what we had to start, right? So it's not this. Does that make sense? You're trying to convert it from one version to another version, but you have to make sure you convert it correctly. Once you're here, log base E 39 equals X, then you can figure out what's on the left-hand side using your calculator. Because now we have an expression for X. X is just equal to this. So I also told you last class, what is log base E? That's a special log, right? It's the most special log. Log base E,
Natural log.
that's the natural log. So this is really the natural log of 39. And now what we do is we just get our calculators. I showed you last time where that key is. Excuse me. Natural log of 39. I do that on my calculator. I get about, I don't know, 3.66 is X. Let's do the next one. Maybe you'll see, you'll catch on to this. I get a feeling that y'all are not getting this, but it could be wrong. What's going on? There we go. So for this one, I'm going to try and solve for X. So I need to isolate the part that's raised to the X. I need to get that by itself, the E to the X by itself. So first thing I'm going to do is take 3 away. When I do that, I'm still left with 5 E to the X. And when I take away 3 from that, I get 1238. Very much like the previous problem, right? Very much like this one. Just take 3 away from both sides. What's different though is we have a 5 in front of the E to the X, and I need to get that out of there because I'm trying to get this by itself. So how could I remove that 5? What do you think?
Divide
Can
it.
you divide
5.
both sides by 5?
Yep, just divide both sides by 5. Good. Okay, it'll go away here. We'll get E to the X. Okay, great. We've got it by itself. And then I've got to get on my calculator and do 1238 divided by 5. And I get 247.6. Now I'm trying to solve for X, right? I am trying to solve for X, but X is up in an exponent. The only way to solve for X when it's up in an exponent is to convert this to a log. So I'm going to now try this again. I'm going to do log and then equals. And basically what you have to do is fill in these 3 things. What's this? What's this? And what's this? You got to fill in those 3 pieces. All of those pieces are going to come from here. So the base will be the E, because that's the base we have up there, E, right? That's the base. What are we raising E to here?
X.
X again. So I'm going to put the X over here because the loop, right? The loop idea that this side is what I raised that to. And that must equal this number, 247.6. And if you're ever unsure, just do the loop real quick. E raised to the X equals that. E raised to the X equals 247.6. Check, because that's what I had here. But the left side, because it's log base E, the left side really just becomes the natural log of 247.6 equals X. And then again, I get on my calculator and I do natural log of 247.6 and I get approximately 5.512 or something like that. Just round it 2 or 3 decimal places. Does that make more sense? Is it clear? Do I need to go through any others like that? We're going to do more of this. I just want to make sure that you've had an okay time with the homework. We all right?
Yeah.
Yes.
Okay. All right. So now I want to do one more word problem like we did last time, and then we're going to move on. We're going to continue, but we're going to move on. All right. We're going to continue doing logarithms is what I'm trying to say, but we're going to have to move on to some new material. Okay, so here. So we had this problem last time. This was a problem from like before the test, okay? So if you put money into an account at a certain interest rate, how long will it take you to have 5,000? Oh, actually, this is the problem we did last time. What I'd like to do is change this problem again. Okay, and what I'd like to do is this. I'd like to ask you if you put, I don't know, let's go with the nice number, $5,000 into an account for 6 years. All right. How or what interest rate would you need to double your money in that time? All right, so this problem is different than the one before that we did last time. All right, so let's just try and put our heads around what's going on here. First, we need to realize we're going to be using the shampoo formula. And with the shampoo formula, A, P, R, and T are all things we need to figure out. The only thing we don't have to worry about is the E, because E is a number. We don't need to worry about it. Okay, so can you all help me here? We're going to put $5,000 into an account for 6 years. What does that tell you? What is the 5,000? What is the 6 years?
Principal.
Principal, or the P is the 5,000, and the 6 years is your
Time.
Time, right? T. Okay, so we have two of the 4 things we have, right? There's 2 of the 4. So right now I could write this: A equals 5,000 E to the R times 6. All right, that's just coming from the first sentence, right? Now it wants to know what interest rate, right? So the thing we need to know is in green here. What interest rate? So isn't that R? That's what we want to know. What would our interest rate need to be to do what?
To double.
To double your money. What does doubling your money mean to us? Think
Twice.
about that. What's
Like
that?
10,000.
10,000, right? We want at the end to have 10,000. So in our equation, what is the 10,000? The A, right? We want the amount at the end to be 10,000. See, everyone, we're doubling our money, so we're going from 5,000 to 10,000, right? So I can actually fill in the left side of that equation, which gives us a final equation that looks like this: 10,000. That's doubling my money. I want that to happen when I start with 5,000. And I leave it in there for, I'm going to put 6 times R instead of R times 6. I'm just going to put 6R. And look at that. Isn't that an equation where the thing you're trying to solve for, R, is up in the exponent? Do you see that? So help me out. How are we going to do this? We need to get this by itself first. So what's my first step?
Divide.
Divide by
5,000.
5,000, right? Okay, good. We divide both sides by 5,000. This will give me 2 on the left side. And on the right side, e to the 6r. Now what?
You have to get the exponent by itself.
Okay, so how are we going to do this? How do we take this and somehow get that r to come down?
Square root.
Oh, careful. What were we doing in the previous problems? Like on this one, we were trying to solve for x. How did we get that x out of there?
Oh, we do the log.
We do a log, okay? That's the big thing here. This is a new way of solving equations. Anytime we have a variable up in the exponent, we always want to be thinking log, right? So I'm going to convert this to a log now, which means I need log. I need to fill in this piece, and this piece, okay? So what's the base? What number goes there?
The e.
The e, okay, that's the thing that's being raised. All right, good.
And then 2.
What's that? 2?
2.
You want 2 here, and then on the other side, careful,
The 6r.
the whole thing, 6r. Does everyone see that? We're recreating, we're taking this and we're creating the logarithm from the expression. We double check with the loop. E raised to the 6r would be equal to 2. Yes, that's the original problem. Now the left side is log base e, so we know that's natural log of 2 equals 6r. So I get on my calculator, I convert, I do natural log of 2 on my calculator. I get 0.693 equals 6r. And last step, we didn't have this step in the previous 2 problems. What's the last step here? Trying to get r.
Divide both sides by 6.
Divide by 6. There we go. So divide that by 6 on your calculator, and you get 0.115. I'm going to round it to 6 equals r. That's our answer, yes? So we go back and think about what it was asking, the question. If you put $5,000 into an account for 6 years, right? Into an account for 6 years, what interest rate would you need in order to double your money in that time? And our answer was 0.116. So what should I put up here for my final answer? Should I put 0.116?
Could you put 11.6%?
Exactly. We're going to put 11.6%. We're going to convert that interest rate into a percentage, because whenever we talk about interest rates, or we're going to convert that R into a percentage, because when we talk about interest rates, we always talk about them in percentages. 11.6% is a very high interest rate. You're never going to find that ever. But that's what you would need. If you wanted to double your money in 6 years, you'd need an 11.6% interest rate. Just out of curiosity, I wonder if anyone can figure this out without doing any of the math. What if I change the 5,000 to 50,000? Would we need a different interest rate
If you wanted to
No.
double it,
to double
no,
your money?
no, it would be the same.
It'd be the same. Think about this, everyone. If I change this right here, oops, whoa, what happened there? If I change this right here to 50,000 instead, then the other side will become 100,000, wouldn't it? And when I did this division, I would still get a 2, wouldn't I? No matter what, like if I had 50,000, I want to double it, become 100,000, I'd always divide by the 50,000 and get 2. Even if I started with $1 million, if I wanted to double to make it 2 million, that first step would still be to divide through. And so if you're trying to double your money, this will always be a 2. Does that make sense to everyone? That this would always be a 2 if you're trying to double your money? So I mean, that's kind of weird. If I put $5,000 into an account for 6 years at 11% or 11.6%, I will have 10,000. But if I put $1 million in 6 years at that same interest rate, I'll have 2 million. So it doesn't matter what you start with. Now, what if I wanted to triple my money instead of double? What if I wanted to triple? What do you think? What do you think would happen? Instead of having a 2, what do you think we would have?
A 3.
A 3. And if we wanted to quadruple our money, we'd have a 4. Does that make sense? It's kind of an interesting thing. It doesn't matter what you start with. If you're trying to double your money, it's going to take everyone the same amount of time. All right. So how do y'all feel about this? Do y'all feel like if I gave you some word problems, you'd be okay with it? I'm seeing some.
Yes.
Yes.
Yeah. Okay. What we'll do is at the end, I'll give you some problems to work. We need to kind of move on. I want to go back to last class. There were properties that I gave you for logarithms. Remember these properties? Gave you 4 properties. I said, we need to know these, and that these are real important. We use this one a lot, right? This one too. But what I need to do is I need to add a few more properties. All right. There's a couple more properties of logs that we're going to need. Okay. So here we go. So more properties of logs. Now these properties are a little confusing to people. So you'll have to see it in action. I gave you 4 properties, so I'm going to pick up now with the 5th property. We'll call this the 5th property. Okay, this property says this. If you ever have a logarithm, and it doesn't matter what the base is, this works for any base, all right? This property says that if inside here, this piece, if it is something times something, if you have 2 things multiplied together, then what you can do is you can split this up into 2 logarithms with addition between the 2. Now, here's what I don't want you to think about it like we're distributing or anything. That's not what's happening. This is just a property of logs. Anytime you have multiplication inside of a log, you can split it into 2. Now, since this works with every log, when we look at the special log that we like, right, the one that we use a lot, the natural log, this property looks like this. So if you take the natural log and you have 2 things being multiplied, you can split it into 2 logs. Now the 6th property is, what if you have a log and inside of it you have division? What do you think?
That will be minus.
It'll be minus, that's right. It'll just be log base A of X minus log base A of Y. So it becomes, if you have division inside of one log, it can split into 2 logs with subtraction between them. And specifically with the natural log, the one that we use so much, this property looks like this. Okay. Now we're going to do something. Give me a moment. I got to pull it up. I had to restart my computer. So I had it open, but I lost it. So give me just a moment. Where is it? Where's the packet? Where the heck is the packet? Sorry for the delay. I'm having trouble finding this file. There we go. All right. Okay, this is going to be continuing with what we've been doing, all right? In terms of working with exponential and logs. Ooh, that didn't come out too good. Okay, we're going to solve some log equations right now. So we're going to kind of like with your homework, okay? With your homework, I gave you some equations to solve. We're going to be now solving what are called log equations. Now, the reason you know these are log equations is because when you look at the equation, it has a log in it, a logarithm. Okay, so we're going to start with that first one. What we want to do here is solve for x. Okay, I want to know what x is. So right now, do you see that the x is inside the logarithm? Right, you have a log and then inside the parentheses, there's an x. We need to get the x out of there. Kind of like with your homework, the x was up in the exponent. We need to get it out of the exponent. Here, the x is trapped inside the log. We need to get it out of the log. So what we're going to do is we're going to convert this using the loop. All right. So if you were to use the loop here, what would you write down? Someone tell me what equation I can come up with from using that loop.
7 to the power of 1 is equal to x minus 2.
Exactly. So using the loop, we know that we take this base, we raise it to this power, and then we set it equal to this. So 7 raised to the first power must equal x minus 2, which is everything that's here. And now this equation's, I hope you would agree, this equation is easy to solve, right? This is a nice little linear equation. We just add 2 to both sides, and we get x is 9. And we're done. So if we plug 9 in there, it should give us a solution. I'm going to check my work just to show you why it works. If I take my original problem and I replace this x with 9, I get 9 minus 2. And the question is, does that equal 1? All right, well, log base 7, 9 minus 2 is 7, that equals 1, that's the question. So now just think about this with the loop. 7 raised to the first power, is that 7? Do y'all see the little loop there? 7 raised to the first, is that 7? Yeah, right? So this checks. Let's look at the next one. Let's do this one. 2 log base 7 x minus 2. So 2 log base 7 of x minus 2 equals, was it 1? Yeah, equals 1. Okay, this problem is very similar to the last one, right? I mean, those are almost the same problems. There's one slight difference. What's the difference between these two?
There's a 2 in front of it.
Yeah, we've got a 2 in front. So let's see, how are we going to handle that? This is critical step, critical step. You cannot use the loop right now. You can only use the loop when what you're looking at is that looks like this. You have to have the log by itself. You can't have anything in front of it. This has to be like a 1. So right now I need to get rid of that 2. So to get rid of the 2, I'm going to divide both sides by 2. The 2's will cancel on the left. Now I have a log by itself. But the right side is now the fraction 1/2. Now you can do the loop. Okay, now you can do it. So when we do this, it's not going to be 7 raised to the 1 anymore. It's going to be 7 raised to the 1/2 equals the x minus 2. Now we have to do 7 to the 1/2 on our calculator. If you want, you can go 7 to the 0.5 if you want to use the decimal instead. Calculator. We've learned already how to do this on our calculator, 7 raised to the 0.5. You should get about 2.6. I'm getting about 4.6, something like that, is equal to x minus 2. And then the last step would be to add 2 to both sides. So if you do that, you should get a final answer. X is approximately 4.646. Now I won't check my answer this time. But that should be, if I plug this in here, everything should work out in the loop. So just be careful. If you have a number in front, you have to address that before you do the loop. Okay. All right, you ready for the next one? Any questions? Yeah, let's do, you know what? I'm gonna do my own. I want to put it all together here. What if we have 4 log base 5 of x plus 3 minus 3 equals, let me go with 12. Okay, I'm going to let you try this first, all right? And I'm going to give you a hint first on how to do it. You're trying to get this all by itself on one side of the equation before you do the loop. Okay, so try and get that whole log thing alone. So move things around, divide through. Once you get it alone, then do your loop, and you'll need your calculator and see if you can get it, all right? I'm going to give you a few minutes. Let's say I'll give you 5 minutes. Let's see if that's probably enough time, hopefully. If you get that one, then try this one. I'll give you another 2 minutes on that first one. Okay, let's see. Grace, did you get the first one? Uh-oh. Hallie?
When you say the first one, you mean the
blue
whole
one.
answer, right? Okay.
Yeah.
Yeah.
You feel okay
I
with it?
got. I think so. Yeah.
Okay, so will you help me walk through it with me? What'd you do first?
I subtracted or I added 3 to both
Good.
sides.
Okay, and so you have 4 log base 5 x plus 3 equals 15.
And
Is that what you
then
had?
oh
Mhm.
yeah, and then I divided the 4.
Good,
on both
divide
sides.
4. Good. So now you have log base 5 x plus 3 equals, use your calculator.
Yeah, I got 3.75.
Okay, good. And now the critical step. So did you convert this with the loop?
Yeah, I did.
Okay, so what did you write?
5 with an exponent of 3.75 is equal to x plus 3.
Perfect. Good job. Okay, now you had to do that on your calculator. Did you have any issues with that?
No.
Okay, so you're comfortable with your calculator?
Yeah.
With this? Okay, so what'd you get on the left side?
On the left side, I got 417.96.
Okay, that's good. And then you're down to one last step.
And then I subtracted 3.
There you go. That's it. Perfect. Did everyone understand that? Anyone have any questions over that?
Yeah, I do.
Okay,
The way I did mine, I first divided by divided both side by 4.
okay,
Yeah, before I added the 3 to the other
gotcha.
side.
All right, now, if you did that, you can still get it right, but you have to divide through by the 4 the right way. So my recommendation is to, if you have, see here we have multiplication, right? And here we have subtraction. I recommend you always take care of this first. After you do that, then you go and do this second. So watch, let me write down the original problem. If you divide it by 4 first, which you can do, but I highly recommend you don't, you would have to do 4 here, 4 here, 4 here. Did you do 4 on all 3? Or just on that 12?
On the 12, yeah.
Yeah, so that is gonna, see, if you don't do the 4 here, then this goes away, that becomes a 3, and then when you added 3, you got 6 on the other side, didn't you?
Yes.
Yeah, and see, that's not gonna work.
Okay.
Because when you divide an equation by a number, you have to divide everything on both sides. And so you just did this and this, but you skipped that. To do it this way, you would have to have done this also. And then you would have had decimals, but it would have worked. You know, it's just, I think you get yourself in a little more trouble this way than if you just move that 3 over first.
Okay.
Good?
Yeah, I did the same thing.
Same thing? Okay, yeah, that's why I gave you this problem. I wanted to just show you that when you have the task of getting that thing by itself, if you have a multiplication and an addition or subtraction, always take care of that addition subtraction first. Think of it this way if it helps you. If I gave you this equation, a linear equation, I asked you to solve for x, wouldn't we add the 3 first? Like, does that seem more natural to you that you would add the 3 first here and then divide by 4?
Yeah.
That's
Yes.
kind of what we're doing, but it's the whole thing here we're trying to get by itself. Do y'all see that? It's kind of like, that's kind of like the x's here. So we add the 3 and then divide by 4. So let's do this one. If we add 3 to both sides, we get 4 natural log of x plus 3 equals 15. Same as the last problem. That's the same first step. Now we divide by 4. And so you get natural log of x plus 3 equals 3.75. Same as the last problem. Here's the part that students will get tripped up on. You're supposed to use the loop, right? At this point. But like the last problem, it's obvious, well, hopefully it's obvious, that the base of this log is 5. So you go 5 raised to this equals that, right? That was the loop. But for this, the base is not here. So we have to remember what the base is. And so do you all remember what the base of the natural log is? This went back to that whole typewriter thing. Remember I told you like typewriters, we didn't want to put that base there each time. So we just agreed we'd write it a different way. So what is the actual base of the natural log function?
E. Is it E?
E. It's E. So just imagine that there's an E here, okay? And then do the loop. Good. E to the 3.75 equals x plus 3. Now we do e to the 3.75. So there's really the only difference in this problem from the one that we just did is that instead of doing 5 to the 3.75, we're going to do e to the 3.75. That'll give us a different number over here. We'll get 42.52 equals x plus 3. Then we subtract 3 on both sides and we get 39. Subtract 3, subtract 3. Get 39.52 equals x. All right. Now I've given you the basic idea of how to solve equations that involve logarithms and exponents. All right. If we go back and we look at what we did for homework, right? What you did for homework, all these problems, the x was up, the variable was up top, right? So the whole idea was try and get this by itself, right? Get that by itself, and then kind of generate the logarithm from that, right? You isolate the parts in red and then generate the logarithm. The problems we just did, these problems are all log problems. And what we do is kind of the same. We isolate this, we get it by itself, and then we use the loop, right? It's the basic idea for both. There's 2 different types of problems, and you have the basic structure of how to do each one. Your homework, I want you to go back to the packet. I want you to look at page 199. I want you to try and do every problem on that page. I'll show you what it is. I'll bring it up here. I won't be able to show you all of them. They won't all fit on the screen. But all of these problems are one of the 2 problems that we just did. So like, for example, the first problem here, right? The x is up in the exponent. So you're going to want to convert that to a log, right? A problem like this, the x is inside the log. So you're going to want to use the loop to turn it into, like the problems we just did, turn it into an exponent. So you've got to be able to look at these and identify what to do. And these are going to be a little more challenging than the ones we did in class. They will. So I'm hoping you'll have some questions for me next time. Also, I need to point out here, where is it? There's one problem on here. I'm just going to remind you that if you have a log equation like this, and the log is not written there, did we talk about what that base is? We know that natural log, that the base is actually an E, right? But if you just write log, what's the base?
10.
10. Okay, it's a 10. So if they don't put the base there, then you need to understand it's a 10. If they put natural log, you need to understand that's E. So that'll help you on a problem like this, because on a problem like this, you're going to need the loop, but you got to know what the base is to do the loop. And these two, number 20 and number 19. All right. Y'all think y'all can handle that? See how it goes? All right, we'll see, right? We will see. All right, now the last topic here for today, and we've got about 20, 25 minutes. The last topic that I want to discuss here is I'm going to do one specific example of where exponential functions come up in the real world. And we've already done one. We've seen the formula A equals P e to the RT, right? We've seen that formula. This is the simple interest formula. That's one example of where exponential functions come into the real world, right? You want to figure out how much money is in an account after a certain amount of time at a specific interest rate. But exponential functions come into play in a lot of different places. And one place that, I have like all these different things I can choose from. The one that I want to do is what we call exponential decay, right? So we have talked about the graphs of exponential functions, but I want to talk about specifically exponential decay and how this relates to something called carbon dating. Have y'all ever heard of carbon dating before? Anyone here? Nix, I see you shaking your head. So let me try and explain it, all right? When anything that is living, okay, whether it be an animal, a human being, or a plant, anything that's living has a certain amount of what's called carbon-14 in it. So here I am, right? I'm alive today. Good for me. And so right now, my carbon-14, I have it in my body. If you were to take a test, you could go into my bones. You could take a biopsy of my bone and you could measure the amount of carbon-14 that I have. So I've got carbon-14 in me. And right now, because I'm alive, I have 100% of it because my body creates carbon-14, through sunlight and other things. We won't get into that, but I've got my carbon-14. As soon as I die, okay, as soon as my life functions begin, cease, right? Then my body can no longer generate carbon-14 because I'm dead, right? So what happens is that the amount of carbon-14 in my body starts to slowly decline, all right? And it takes time for it to go away. So if I die right now, right? And then, later on today, my body's in the morgue and they do a carbon-14 test, I'm going to have a lot of carbon-14, but I'm not going to have 100% of it because I will have died a few hours ago. So we can use the amount of carbon-14 in a bone or in a body or whatever to figure out how long ago it died. So if I find a bone, if someone's digging and they find a bone, they go, oh, let's go test the carbon-14. They find just a very, very small amount. They can actually figure out, it's an estimate. It's not perfect, but it's an estimate as how old the bone is. And it's all dependent upon this, exponential decay model, all right? So that's the general idea of carbon-14. I got to build some more stuff up to it. So we need to talk specifically about carbon-14. Okay, carbon-14. So carbon-14 decays over time. So as time goes on, like I said, once you die, your body stops producing it and it starts to decay. So if I were to draw a picture of what's happening here. When I die, let's say that's time 0, I would have 100% of my carbon-14. And then the carbon-14 starts to drop away over time. And this the graph of how it drops, this is an exponential function. And so with an exponential function, we know that as time goes on here, it gets closer and closer to 0, but never gets there. So that means there will always be some small trace of carbon-14 somewhere in that bone. So what we need to know in order to figure this problem out is something about the carbon-14, something specific, something we call the half-life. Have y'all ever heard of half-life before? Not the video game, because I know there's a video game called Half-Life. But half-life is actually a physical principle. So think of it this way. I like to do this with a piece of paper. Let's say that this is all the carbon-14 in my body. This piece of paper represents all the carbon-14. With carbon-14, it takes a certain amount of time for half of it to go away. All right. So you know what? Let's look it up. I'm going to look it up on the web. I'm going to look up the half-life of carbon-14. I think it's 36,000 years, but I'm going purely off memory here. Let me see here. Whoa. Okay. Carbon-14, 14 half-life.
5,700 years roughly.
5,700 years. I don't know where I got 36,000 from. Okay.
Some people
Yeah,
say
5730.
5730.
Let's go with 5730. The half-life of carbon-14 is 5730 years. Okay, so wrap your heads around this. All right, this is pretty crazy. If this is all the carbon-14 in my body, right, when I die, this is all of it, then in 5,730 years, half of it will have decayed and gone away. All right, it took 5,730 years for that to happen. Then 5,730 years after that, half of that goes away. And then 5,730 years after that, half of that goes away. And then 5,730 years later, half again. 5,730 years later, it goes half again. Another 5,730 years, half again. Is this ever going to be gone? If I keep cutting it in half, will it ever completely be gone? Nope. It's still gonna, I'm still gonna have something there, right? But each time I'm tearing this, it's 5,730 years. Okay, that's a long time, right? That is a long time for half of it to go away. So here we go. So let's now try and build up the formula we're going to use to be able to answer something. The ultimate question here is I'm going to tell you that we found a bone, and I'm going to tell you how much carbon-14 is in it, and you're going to tell me how old the bone is. All right. So the first thing we need to do is come up with the exponential function. Okay. So the exponential function, here's what we know. That exponential function, f of x, must be equal to, well, it's got to be an exponential function. So what I'm going to put here is, I'm trying to think of what I want to use here. Yeah, let's use capital A e to the RT. Oh, you know what? Let's use P. Let's use P. It's gonna, that way it'll look like the shampoo formula, and it won't look like I'm creating something new. This is something we've used before. So oops, I need to make the T and X, sorry. Because I'm using X here. So we know that this exponential function is going to look like this. What we need to figure out, all right, what we need to figure out is what R is. Now, you know how R for the money in the account, that was our interest rate. Here, the R is going to give us how quickly the carbon-14 is going away. Okay, how fast it decays. So here's how you get R. So our goal here is to find R. To do this, here's what I know. At x equals 0, that's when the person died. All right. So at time equals 0, that's when the person would die. How much, can you tell me how much carbon-14 would be there? Well, what did I say? When you die, 100% of your carbon-14 is there, right? 100%. So 100% is there. Now I'm going to convert 100% to a number. 100% is 1, right? I just move the decimal point 2 places to the left. So I've got 1. Y'all understand that? At time equals 0, when whatever it is dies, whether it be a human or some, wildebeest or something out in the Serengeti plains, whatever it is, it dies. It should have 100% of its carbon-14 there. So if I measure it, it should be 1. So look, take the function and tell me what happens. When I plug in 0, I need to get 1, right? That's what this says. When we start at 0, I need to get 1. Yes? So plug 0 into this function and tell me what you get. F of 0 is P E times R. Now I'm replacing X with 0. And this gives me P E, R times 0 is 0. And what is E to the 0? Any number raised to the 0 is what?
1.
1. So this is P times 1, which is P. All right. So when I plug 0 into the function, I get P. Yes? But what does that need to be equal to? It needs to be equal to 1, right? So when I plug 0 into the function, I need that to be equal to 1. So can you tell me then what P is? P has to be 1, right? We're saying when you plug 0 in, you get P, but that has to be equal to 1, so P must be 1. So what does your function look like now? This function, I know that P is 1. So when I plug in, when I write the function, I know P is 1. So now the function looks like this, e to the Rx. I know this is confusing, but let me just continue. At X equals 5,730, how much carbon is there? How much carbon-14 is there?
Half of what there originally was. It's
Half of the original. Now, the reason I know that is because I know that the half-life of carbon-14 is 5,730 years, because researchers have measured it and stuff, so they know that's how long it takes. So we should expect to see 50% of the carbon-14 there, which is really the number 0.5 written as a decimal. So that means when I take 5,730 and I plug it into my function, I better get 0.5. Right? When I take this is the equation we have right now. When I plug in 5,730 into this equation, I better get 0.5. So that means when I take 5,730, plug it into that equation, e to the R times 5,730, what does it need to be equal to when I plug that in? When I plug this in, what does it need to be equal to?
1, right? Or 0?
That was this one. That was up here. We
Okay.
said that the function, when you plug in 0, you better have 100% of your carbon-14, but 5,730 years later, you better have how much?
Is it 0.5?
0.5. So we need this to be equal to 0.5. So look at that, everyone. Look, we have e to the 5730r equals 0.5. Wait a minute, isn't that just an exponential equation? Can you solve for r if I asked you to right now?
Yes.
Yeah, you could create a log from this, couldn't you? You could go log, what would the base be? Do the loop. Think about the loop. You'd have e here, right? What would be on this side? The right side of the equal sign.
The 5,730 have?
Yep, 5,730R. And then here it would be 0.5. Now log base e is natural log. So you go natural log of 0.5 equals 5730. And then I'm just gonna use my calculator now to figure out what natural log of 0.5 is. I get negative 0.6931 equals 5730R. And I have one last step. I have to divide by 5730. And I'm gonna get an answer here for R, and it's gonna be a crazy small number, but watch, I'm gonna use as many decimal points as I can. I'm gonna use what my calculator gives me here. It is 0.000120968. That's what I'm going to use for R. We're almost there. We're not answering the question yet. We're almost to this final thing that I'm going to give you, and then we'll be able to answer a question. So here's what I know about my function. My function is equal to e, but now I know what r is, don't I? R is this number, negative 0.000120968x. And this right here is the master formula for carbon 14. You should write that down. I will allow you to have a little reference sheet on your next test, right? And I think you need to have this. I will not necessarily ask you to go through and prove it all and figure out the formula yourself. This is how you do it. All you need to know is this is the formula and we need to be able to use it. The reason I showed this to you is because you can actually use this formula for any sort of anything that has a half-life, whether it be carbon 14 or some radioactive material, doesn't matter. This is how we determine the function for it. So let's now get to a question, all right? And I've only got about 7 or 8 minutes. A bone is found to have about 0.2% of its carbon 14. How old is the bone? Okay, so a bone's found, take it to a lab, they measure it. It's got about 0.2% of its original carbon 14. All right. How old is that bone? So here's what we're going to do. We're going to use the function that we just generated ourselves here. We're going to use this. This is how we determine everything for carbon 14 now. All right. Now, I just want to remind you that X here in this formula, X is the time in years and f of x is the amount of carbon 14. In other words, for this function, you plug in x is the time, how old something is. And what the function spits out is how much carbon-14 is there. Is that clear to everyone? X goes in as time. If you look at this as a function, time goes in, amount of carbon-14 is what comes out. So look at the problem that they're giving us. A bone is found to have 0.2% of its carbon-14. How old is it? Is this question asking us how much the amount of carbon-14 there is, or the time it took to get that much? Which of these two is it asking for?
The time.
Yeah, how old the bone is, right? We want to know what the time is. So we're trying to figure out what X is that creates this much carbon-14. So what you're going to do is you're going to take your function and you're going to replace the left side of the equation with 0.002. Okay, why am I doing that? What is that?
Converting it to a decimal.
Yeah, this is the amount, right? This is the amount of carbon-14 I have. Oops, amount. Oops. This is the amount of carbon-14 I have. I need to convert that percentage to a decimal. So I convert it. That must be equal to e to the negative 0.000120968x. And now what I need to do is find x. And everyone here now should be more comfortable with this idea. I'm going to first create a log. So I create a log. The base of this log is e, because that's the base here. Then my equals, okay, e raised to, okay, what goes on the other side of the equal? All that crap over there, right? Negative 0.00012096.8x. And then in here goes 0.002. Check it with the loop. E raised to that equals that. Yep, that's the original equation. On the left side, that's natural log. So I'm going to need my calculator. So I'm going to do natural log of 0.002. I get 6.2146. That's good enough. Equals negative 0.00012096.8x. Last step. Last step.
You
Solving
divide.
for x, right? Divide both sides by that 0.00012096.8. Negative 0.00012096.8. Someone can help me confirm. You get something around 51,373 is approximately what x is. Did anyone else get that?
Yeah,
Yes.
that's what I got.
That's how old the bone is, approximately. That's how we do carbon dating. Now, there's a lot more to this. I mean, you have to be able to measure things and things like that, but the math behind it all comes down to this equation right here that we came up with. The only thing we needed to come up with that equation was the half-life of carbon-14. The half-life of carbon-14, that's all we needed. So what I'd like for you to do along with your homework is I'd like to offer you a problem here, or I want you to try a problem for homework. Same thing here. A bone is found, okay, but let's do it this way. A bone is found to have, let's go with let's go with a very small number, 0.005% of its carbon-14. How old is it? Okay, and now let's let that be question number 1. And then I'm asking you a different question to see if you can figure this out. A bone is 4,210,000 years old. How much carbon-14 does it have? Those are two different questions. The first question is asking how old a bone is if you were able to measure the carbon-14. The other one is, I'm telling you how old it is, and I want to know how much carbon-14 it would have. Okay, it's the end of class. Just a reminder, next week, I already told you all about next Thursday, right? Did I tell you all about? No? Y'all are looking at me.
Yes.
Yes, the
So
11th.
next Thursday, my wife's having surgery in Houston and I'll be out of town. So my intention for Thursday is to put something together for you to it's like going to be an assignment that you do. It's probably going to be a video. I won't make it an hour and 50 minutes long. It'll be like a short, maybe 20, 30-minute video or something with an assignment to go with it. All right. And that will be in place of class. We won't have class because I don't think it'll be worth us having a sub come in and then everyone will be confused because the sub did it different than I did it. And so look at Thursday as you won't have to be in class. Okay, like you won't have to be here, but there will be something you have to do and turn in. And I'll let y'all know more about that early next week. But I will be here on Tuesday. Okay, Tuesday we will have class. Okay, everyone, do those problems that I gave you off page 199 along with these two. Come with questions. Have a great weekend.
Thank you.
Thank you, you too.
Bye.
Bye-bye. Have a good one.
You too.
Emily, that got dark fast.